Welcome to Aqueous Equilibrium Part 2. So today we're going to look at pH titration curves, and this can be kind of daunting because there's a lot of different points along a pH titration curve where we can calculate pH, and depending upon the types of species that we have involved in the titration, we can do any number of different types of calculations. So what I'm going to spend some time with you today is just going through these calculations. So here are our objectives for today. So we're going to define the various types of pH titration curves that you could run across in an acid-base titration. We're going to understand how to calculate the pH along any given point in a titration. We're going to identify the type of titration from the pH titration graph. So if I show you a graph, you should be able to identify what type of pH titration that is. And then we're going to learn about indicators that we're going to use in titrations. And just to back up just a little bit to remind you that we're talking about, we started this chapter, we're talking about the formation of buffers and how a buffer is a conjugate acid-base pair. And that's going to come into play when we look at pH titration curves, because depending upon the species that we have, whether it's a weak acid or a weak base, you can form this region of the pH titration curve that's going to have a buffer region. And so we're going to come back to this idea of buffering. Okay, so just to introduce titration, I'm sure everybody has done a titration. So you have generally something in a flask, and then you have the titrant. So the analyte is in the flask, and the titrant is going to be in the burette. And oftentimes we have the acid in the flask in an acid-base titration, and we're titrating in the base. But that doesn't have to be the case. So you can have the acid in the burette and your base in the flask when you do that titration. It's just going to depend upon where you're starting pHs. So if I start with acidic solution in my flask, then I'm going to start at a low pH, and as I titrate in the hydroxide, my pH is going to go up. So I'm going to expect that graph to look very different if I had hydroxide, my base in the flask, and then I was titrating in acid. So then I would start at a really high pH, and I would see my pH go down. At any rate, it's really hard, unless you're monitoring the change in pH, it's oftentimes awkward to figure out when you've reached your equivalence point. Remember, the equivalence point is the point at which you've reacted all of the analyte that's in your flask with the titrant that's in your burette. And so we use indicators, and they are sensitive to pH, and so they'll change at particular pHs. And this is an example of phenolphthalein, which is one you probably used a lot in the lab. Phenolphthalein is very sensitive to excess hydroxide ions. So when you start to see that color change for phenolphthalein, you're just a smidgen past that equilibrium point, the equivalence point. Okay, so we're going to look today at titration curves. And titration curves are a plot of pH versus the amount of titrant. So whatever you have in the burette. So my curve is going to have my pH on the y-axis, and then my x-axis is going to be the volume of whatever it is I'm titrating into the flask. And so oftentimes we have the base in the burette, but that doesn't have to be the case. The pH can be calculated at any point during the titration, and the shape of the pH curve is going to depend upon the strengths of the acids and the bases titrated. This is not a complicated topic, but the calculations can get complicated. And I'm actually going to do some calculations with you today in this part of our pre-recorded lecture here. Okay, so let's look at the various options that we have for pH titration. I can have a pH titration that is a strong acid plus a strong base. And these are something you've probably done in the lab a lot. These are very common general chemistry types of titrations where my strong acid might be HCl, and these are aqueous solutions, and my strong base might be sodium hydroxide. We also call these acid-base neutralizations. So all of the reactions that we're going to talk about today, all of these pH titrations are going to be acid-base neutralization reactions, where I'm neutralizing the acid or I'm neutralizing the base with its counterpart. If I have a strong acid, strong base, my products of this are going to be water and my salt that's left, sodium chloride, which is soluble, so that's going to be an aqueous solution. So strong acid, strong base, and I'm going to, at my equivalence point, I've reacted all of the acid. I've added in enough base to react all of the acid. So I can have a weak acid plus a strong base, And let's say our weak acid maybe is HF. So an aqueous solution of HF, and I'm going to react that with sodium hydroxide. This is still an acid-base neutralization reaction. So this is not an equilibrium reaction. I know we've been talking about equilibrium reactions. HF, if I just had HF in water, that's an equilibrium scenario where I have partial dissociation. But now when I add in my strong base, hydroxide is going to react with the hydrogen ion here, and it's going to force this to dissociate more. So I'm going to have this equilibrium scenario where for every 1 mole of hydroxide that I add in, it's going to react with a mole of hydronium ion, which is going to force 1 mole of my HF to dissociate. And so I'm forcing the equilibrium of this to be completely disassociated when I've added in enough hydroxide to react to form H2O. So I neutralize this hydronium ion. I'm left with sodium fluoride. So these are not equilibrium reactions. Once I form water, I'm not going to go back. My third option is I could have a strong acid plus a weak base. So this might be something like, we'll use HCl again. And my weak base might be ammonia, NH3. So my products of this are going to be NH4Cl, where I'm going to pick up this hydrogen ion. It's going to bind with my weak base here and become NH4 plus my ammonium polyatomic ion, which is conjugate acid, and then I'm just going to have chlorine ions. So this is going to be in solution. And then the fourth option that I can have is I can have a weak acid plus a weak base. So something like this might be HF plus NH3, and then I'm going to form, and these would be aqueous solutions of both. I'm going to form NH4F aqueous, and where I've neutralized this acid by my base picking up a proton from it. And so each one of these is going to have a unique pH titration curve. So my titration curve, I'm going to set them all up the same, regardless of what I'm reacting with what. My pH titration curve is going to have pH on the y-axis, and I'm going to have volume of titrant down here. And this is going to be usually in milliliters. And pH, remember, is a 0 to 14 unitless scale. And then I'll start with 0 moles of my titrant, and then I'll go to, some amount that is going to exceed my equivalence point. So at the equivalence point, we talk about the equivalence point a lot in this part. At my equivalence point, I've added enough titrant to completely react all of the analyte, whatever's in the flask. Typically, what we're going to look at is we're going to have volume of titrant. This might be my base. And then I'm titrating in with my acid. So all these are going to have very different types of graphs, and the equivalence point is also going to tell us what type of pH curve that we're looking at. So at the equivalence point, the number of moles of acid are going to equal the number of moles of base. One of them is not going to be in excess. There's going to be exactly the same amount. All right, so let's look at the simplest one. So the simplest one is the strong acid, strong base. So in a strong acid, strong base, the pH titration curve is going to look like this. And what you see here is I know that I'm titrating in my base because I'm starting at a really low pH. So at 0 base added, I have a very low pH that tells me that the acid is going to be in the flask. I'm titrating in sodium hydroxide. I'm going to have a really low pH because for every mole of sodium hydroxide I add in, I'm reacting 1 mole of the hydronium ion. And so it's going to kind of move along until I get right to that point where I'm almost right where those 2 moles equal each other. And at that point, that's my equivalence point. So I'm going to add in 1 more mole of my sodium hydroxide. I'm going to hit that equivalence point. What I'm going to see is my pH here is going to be fairly low. And then there's going to be this steep climb in pH. So if I was looking at this in the lab and I was monitoring it with a pH meter, what I would see is very little, it's kind of chugging along and small changes in pH as I'm adding in volume of NaOH. And then at some point, it's just going to shoot right up. The middle of that really steep rise is your equivalence point. And if I have a strong acid, strong base, my equivalence point ends at pH 7 because that's a completely neutral species. So my equivalence point would be right at 7, and then anything that I add after that equivalence point is just excess sodium hydroxide that I'm adding in. And so you'll see this really high pH here, indicative of hydroxide ion that I'm adding into the solution. So there's no more acid for it to react with. So strong acid, strong base is our easiest. You can recognize it from the graph because it has this really flat region here, a really steep point at the equivalence point. Your equivalence point is always going to be at pH 7, and then this pretty flat plateau right after the equivalence point. So that's going to tell you that you have a strong acid, strong base. I'm just going to go through what these look like first, and then we'll come back and we'll talk about the calculations that are going to be involved. If I have the opposite, so let's say I have in my flask is my base and I'm titrating in my acid. So at 0 moles of acid added, I'm going to have a really high pH because that's going to be the pH of my base solution. And I'm just going to see the reverse or the opposite of this other graph. I'm going to have a sloping plateau here, but it's going to be relatively flat. So you can see here, this is over the course of like 1 pH point where I'm going right to here, and then I'm going to have this steep drop. And then my equivalence point I see here is still at pH 7. So strong acid, strong base, your equivalence point is always going to be at pH 7. And then past this equivalence point, I'm just adding in excess acid. And so I'm going to see a really low pH here. This is a graph of a strong acid titrated with a strong base. This is a graph of a strong base titrated with a strong acid. So they look very similar. They both have equivalence points at pH 7. The only difference is your starting and ending pHs are going to be reversed. Now if I have a weak acid, strong base, my titration curve looks very different. You'll see that I have this region here that's sort of resistant to pH change, but is going up, and it has this kind of characteristic sort of hump on it, which looks very different than this region here with my strong acid, strong base. So my weak acid, strong base, this region here is called the buffer range, is unique to this type of system. You're not going to see this in a strong acid, strong base. I'm still going to have an equivalence point. That's that point where my pH is going to rise rapidly, but now my equivalence point is no longer at a pH of 7. So my equivalence point is actually at a basic pH here, and we'll talk about why that is. And then once you get past the equivalence point, this looks very similar to what we saw with the strong acid, strong base, in that this region here is just excess hydroxide. That region should look very similar. So the difference here in a weak acid from a strong acid is you have this buffer region. Your calculation of pH for these pH titrations is going to be a little bit complicated in this buffer range and a little bit complicated up here at the equivalence point. If I have the opposite where I have a weak base and a strong acid, so here I'm starting out with base and I'm titrating in a strong acid, you see here I have this hump as well, this buffer region here where I'm going to have a resistance to the pH change. It's going to look very different than what we saw with our strong base, strong acid. See here you don't have this buffer region, you just plateau region here. So my weak base is going to have that area which is going to be resistant to pH change because it's essentially being buffered. My equivalence point is going to be midway down this steep part here, but my equivalence point now you see is acidic, so it's not a neutral pH. At the equivalence point, it's an acidic pH, and then here is just excess acid that I've added in. I can have a weak acid, weak base, and so what I see is a weak acid, weak base. I have a buffer region here, and then I would also have a buffer region up here. And so we don't really do too much with the weak acid, weak base titration just because the calculations get pretty strenuous with that. So we're going to deal with the first three: strong acid, strong base, weak acid, strong base, and weak base, strong acid. So we're going to look at those three. So let's take the easy one first. Let's take a strong acid, strong base. So I'm going to abbreviate this SA and this SB. And these are all neutralization reactions. So let's say that I have 25 milliliters of a 0.200 molarity HCl solution. And I'm going to titrate that with 0.250 molar sodium hydroxide. So my chemical equation for this is going to look like HCl plus NaOH goes to H2O plus NaCl. So I want to calculate my pH initially, and I want to calculate my pH at a couple of points. Calculate the pH with no NaOH added with 10 milliliters of NaOH added with 20 milliliters of NaOH added. And then my last one will be with 25 milliliters of NaOH added. So I'm going to calculate my pH here. It's going to be helpful to know where I am on my titration curve. So I'm adding in NaOH here, and this is going to be in milliliters. So I want to know my pH at 0, my pH at 10, my pH at 20, and my pH at 25. What I know is since this is a strong acid, strong base, at my equivalence point, my pH is going to be equal to 7 because I have a strong acid and strong base. So it might be helpful to find where my equivalence point is, because I know past my equivalence point, it's just going to be excess sodium hydroxide. Before my equivalence point, then I'm going to see how much hydronium ion I have left. So the first thing is I'm just going to calculate what my volume is that I'm going to need to reach the equivalence point. So I'm going to do this with any titration. So in order to do that, I need to find moles of acid, and then at my equivalence point, number of moles of acid is going to equal number of moles of base, and then I'll find volume of base based on number of moles of base. Okay, so it sounds complicated, but it isn't. Some of the things that I have here is I have 25 mils of a 0.2 molar solution of HCl. So I'm going to take this and I'm going to find moles of acid. That's going to tell me how many moles of acid I have in that solution. So I'll take 25 and I'll divide this by 1,000 and I'm going to multiply it by 0.2 because that's how many moles of HCl in 1 liter. That's going to give me 5.0 times 10 to the minus 3 moles of HCl. Okay, so I'm going to need 5 times 10 to the minus 3rd moles of sodium hydroxide to react all of this acid. And I want to know the volume of the base. So now to do this, I'm going to come up here and I'm going to take my molarity of my base and I'm going to use that to figure out how many milliliters of base I'm going to need to have added in this number of moles of base. Tell me that I need to add in 20 milliliters of sodium hydroxide, and this is to reach the equivalence point. And at the equivalence point, my pH is then equal to 7. I know here, this is where my equivalence point is. So this is my equivalence point. This is before, so I'm going to have excess acid here, and this is after, so I'm going to have excess base here. So my pH here is going to be driven by how much hydrochloric acid hasn't reacted, and my pH here is going to be driven by how much additional sodium hydroxide I have in past what I needed to react all of my acid. Okay, so to find my initial pH, no sodium hydroxide added. So this is a strong acid. So if this is a strong acid, I'm going to take just the molarity of it. It doesn't matter if I have 25 mils or 50 mils or 100 mils. My pH is going to be driven by the concentration of that strong acid. So for A, I'm just going to take the negative log of 0.200 molar, and that's going to give me my pH, 0.699. So that's my initial pH. That would be my pH here with no sodium hydroxide added. Now if I want to know how many after 10 mils, to get to B, what I'm going to have to do is I'm going to have to find how many moles of base I'm adding in. I'm going to take that and I'm going to multiply, I'm going to divide by 1,000 to get it into liters, and then I'm going to multiply that by my concentration of my sodium hydroxide, and that's going to give me moles of sodium hydroxide to the minus 3 hydroxide. This is how much I've added to that solution. That means that this is how much sodium hydroxide is going to react with my acid. So if I want to know how much acid is going to be left over, I'm going to take my initial moles of acid, which I calculated up here, and I'm going to subtract the number of moles of base that I've added in. 2.5 times 10 to the minus 3 moles of unreacted acid still in my solution. Now I can't take this value and take the pH of it. This has got to be in units of molarity. So what I'm going to do is I'm going to say, okay, I have this many moles of unreacted acid. I'm going to find my new concentration by dividing it by the total volume that's in my solution now. So I started with 25 mils. I've added 10 mils. So my total volume then is going to be 0.350 milliliters. And then that's going to give me my new concentration of acid. And then to calculate the pH of that, I'm just going to take the negative log of it. So my pH has gone up, which I would expect because I have less concentration of my acid, but I still have an excess of my acid in there. I haven't reacted at all, so it's still going to be a relatively low pH. At the equivalence point, I already know that this pH is 7, so I don't even have to do any calculations here. And then after, what I'm going to do is I'm going to take that 5 mils, so it took 20 mils to reach my equivalence point. This 5 extra mils here is then just excess hydroxide ion that's being added into that solution. So I'm going to take that and figure out my concentration of hydroxide ion. I have 25 milliliters of base. I took 20 mils to get to the equivalence point, so I have 5 milliliters of base past the equivalence point. So this is what's going to drive the pH at that point, because at the equivalence point, everything had been reacted. All my moles of acid had been reacted with base. Now to find my pH, I need to divide by the total volume. So at this point, I started with 25 mils of HCl, and I've added in 25 mils of base, so my total volume here is going to be 50 milliliters, 0.025 molar. So if I take the negative log of that, because this is hydroxide ion concentration, this is my pOH. It's not my pH. So I'm going to take 14 and subtract this from it. This is my pH at 25 mils of sodium hydroxide added. So what my titration curve would look like, strong acid, strong base. And this is always going to be at 7 for strong acid, strong base. Now if I have a weak acid and a strong base, a weak acid, strong base titration curve is going to look different because I have that area in the beginning where I have a buffer region. So let's say I take sodium hydroxide and I react that with formic acid. 25 mils of my acid, and my acid is a 0.100 molar, and I'm going to titrate that with 0.100 molar NaOH. So my pH titration curve is going to be with milliliters of sodium hydroxide down here. So this is a weak acid plus strong base. So now I'm going to have this region, this buffer region in there. I'm going to find my pH with 0 milliliters of base added. I'm going to find it with 5 mils of base added, with 10 mils of base added, with 12.5 milliliters, and then we'll do 15, 25. I have 0, 5, 10, 12 and a half, 15, 25. It's going to help me to know where my equivalence point is. So even though I'm not asked for that, it's going to help me because I'm going to set up my calculations differently depending upon whether I'm before the equivalence point, at the equivalence point, or past the equivalence point. So even though I don't explicitly ask you to find the equivalence point, this should probably always be your first step. So in order to do that, I need to find moles of acid, because my equivalence point, remember, is number of moles of acid is going to equal the number of moles of base. So to find my equivalence point, I need to find my moles of both of these. So at my equivalence point, I have to have added in this number of moles of base. To reach my equivalence point, I'm going to need to add in 25 milliliters. That is here, right? So this is my equivalence point. So everything before this is pre-equivalence point. So that's going to help me figure out what I'm going to be doing, because that means that all of these here, these titration points here, are in the buffer region. To find the pH using my pH scenario for a buffer, this I have 0 base added, so this is just a standard ice table using my Ka for my acid. And then here we'll talk about our calculation here. This is not going to be a pH equal to 7. It's going to be a basic pH. So it's going to be past 7. I don't know what that is yet. We'll come back to that for calculations. So let's do A first. So my pH is going to be driven by how much of this has disassociated. So I need to look up the Ka for this. So I'm going to set this up like an ice table, as we've been doing. I'm going to go back to my initial concentration is 0.100. I have none of this and none of this at time 0. This is going to go down. This is going to go up. This is going to go up. So my equilibrium, this, and this. My my extra small approximation is okay probably to use here just because the difference in these is 10 to the third. So this is my starting pH, no base added. All right, now once I start adding in base, I have a scenario where I have conjugate acid, conjugate base present, and I'm going to have a small amount of buffering that's going to be happening. When I add in base, it's going to react with this. It's going to shift my equilibrium this way. So once I start adding in hydroxide, the hydroxide is going to react with the H3O plus to form water. That's going to shift my equilibrium of my CH2O2 to CHO2 minus plus H3O plus forward. So I'm going to produce more of this. This will increase, and this is going to decrease. So I'm going to look at my conjugate acid, conjugate base. I'm going to put it into that pH equal pKa plus log of conjugate base, conjugate acid, and I'm going to solve for my pH. So all along through here, I'm going to track the changes in concentration. So every time I add in hydroxide, what's going to happen is this is going to go down. My weak acid concentration is going to go down. My conjugate base of that weak acid is going to go up. And so I'm going to track how this goes down, how this goes up, and then I'm going to use my Henderson-Hasselbalch equation here. All right, so my initial moles of this were, if you remember up here, 2.5 times 10 to the minus. I'm going to keep track of that, how my moles are going to be changing. So my first point is I'm adding in 5 milliliters of base. So let's figure out how many moles of base that is. When I add in 5 milliliters, I'm adding in 5 times 10 to the minus 4 moles of base. Started with 2.5 times 10 to the minus 3 moles of this, and I'm going to assume I started with 0 moles of that, so this is my conjugate acid, conjugate base. Now I'm adding in this number of moles of base. This is going to go down by that value, and this is going to go up. So this is how much base I added. It's going to decrease my conjugate acid by that much, and it's going to increase my conjugate base by that much. So I'm going to take those values and I'm going to plug them into my equation here and solve for my new pH. So I need my pKa. My pKa, remember, is negative log of the Ka. And then instead of putting these into molarity, I can actually just look at these values in terms of moles. So this is the one occasion where I take the log of something. This is a ratio, so even if I divide them both by the total volume, it's going to cancel out. So I can just use moles here. I can't use it in any other log calculation. I'm going to have to get to molarity, but when I'm using this equation here, I can do that. This is going to be the log of the conjugate base. Now notice this is not, even though these values are the same, this is not the amount of base that I've added in. This is the amount of conjugate base that I've created. So this is my second point along that titration curve. My initial pH, once I've added in 5 mils of base, now I'm in that buffer region. Now my second point was what happens at 10 milliliters of base. And what I can do is I can just go back and assume that I haven't added in this 5 and do this calculation all over again. But now instead of this number of moles, I'm going to have the number of moles that would correspond to 10 milliliters of base, or I could just keep a running tally. So I find it can be often confusing if I'm always trying to add on to what I did before. So I might just take this as an independent. So I'm going to pretend like I didn't do any of this and just see where is my pH if I've just added in 10 mils. So I haven't added in 15, I've added in 5 past that, but I'm going to pretend like I didn't do this calculation, and I'm going to do the same thing I did up here, but with this number of moles of base added. All right, D is at 12.5 milliliters of base, and this is a unique point. At this point, what has happened is these two values are going to be the same. I'm at my what I call a half equivalence point. So if it takes 25 mils to get to the equivalence point, at 12.5 mils, I'm halfway there. And at my half equivalence point, my pH equals my pKa because my conjugate acid concentration equals my conjugate base concentrations. If I know my equivalence point and I did that first, I know what my volume is to get there, I don't have to calculate my half equivalence point. I already know it because I know the pKa. So my pH here then is going to be equal to 3.745. E, I was looking at 15 milliliters. So at 15 milliliters, I'm going to have a scenario where I have more base than acid. So here they're equal. Here I still had more acid than base. Here I definitely had more acid than base. So here I'm going past the half equivalence point. So now I'm starting to have more conjugate base than I have conjugate acid. And my pH is 3.745 plus the log, and then this is going to give me a pH of 3.921. So you can see that my pH is going up. At my equivalence point, I'm close to the equivalence point. The next addition of acid that I have on my list here is going to be at the equivalence point. And there something unique happens. I'm going to have reacted, all of my acid has turned into conjugate base. So at the equivalence point at 25 mils, I'm going to have 0 of this, and I'm going to have 2.5 times 10 to the minus 3 moles of this. So that means that I just have CHO2 minus, and I have 2.5 times 10 to the minus 3 moles of that in water. That's all that I have in water, because at the equivalence point I've just added in enough base. I've reacted all of this hydronium ion, and I've basically converted all of this into the conjugate base. So this is my conjugate base. In water, what this is going to do is this is going to pull, this is going to act like a base, it's going to be a proton acceptor, and it's going to reform the conjugate acid, and then it's going to leave hydroxide ion. So this is why at the equivalence point I'm going to have a basic pH, because I have the reverse of the equilibrium that I had at the beginning, where all of my conjugate base now is in solution, and I'm looking at how much of that is reforming the conjugate acid, because that's going to produce hydroxide ion. So I'm going to find my molarity here. So this is going to be an ice table, but I need to convert this into molarities before I can use it in my ice table. So I'm going to look at the total volume that I had. So I've added in 25 mils. I originally had 25 mils of my acid, so my total volume here is going to be 50 mils. So I'm going to divide this by 0.050 liters, and that's going to give me my molarity of my conjugate base. And so this is a Kb because I have hydroxide over here, and my law of mass action is going to look like this. I don't have the Kb. I have the Ka, so I need to find my Kb first by taking my Kw and dividing it by my Ka. And then I'm going to solve for x. I can do my x is small approximation because this is so much greater than 10 to the minus 11. That's going to give me an x value. So when I take the POH is going to be equal to the negative log of that. My pH is 14 minus 778. Which is 8.223, which is basic. So this is the pH at the equivalence point, and I basically solved it by doing this ice table, but instead of finding hydronium ion concentration like we did at 0 base added, I'm doing the opposite. I'm finding hydroxide and I'm looking at a Kb. And then everything I do past that is just going to be excess base added. Way that you're going to set these up, and I've tried to help you here in this equation quick sheet, is on the second page here are all the various titrations. So strong acid, strong base, weak acid, strong base, weak base, strong acid, and then here's my weak base, strong acid, weak acid, strong base. Here are the various steps that you would do depending upon your scenario. So strong acid, strong base, this is the simplest. Weak acid, this is the one we just did. The weak base is going to be the opposite of the weak acid, strong base. And then we're not really going to worry too much about a weak acid, weak base, because we don't really do those types of pH titration curves. I mean, we can and we can do it, but the complexity starts to get really crazy. Okay, so just to finish this has been a long section just because we've done some of these calculations together. It's just to talk about indicators. And an indicator is usually something that's really sensitive to the pH change. And there are a lot of indicators, and these are generally organic indicators. So these are organic acids or organic bases, and they're going to change color based upon the pH that they're in. And so We use phenolphthalein a lot, but you see, phenolphthalein is not the best indicator for strong acid, strong base, which is what we use it for all the time, because it really indicates once you're past pH 7 and you're really into the basic range. And so for strong acid, strong base, maybe something like methylphenol red or bromothiamyl blue might be better, right? Because then you're going to start to see this green to blue color change right at around 7. So there's lots of different indicators that we can use depending upon the titration curves that we're doing. If we're doing a weak acid, strong base, we might want something in the acidic range because our equivalence point is going to be acidic. If we have a weak acid, strong base, we might want something that's in the basic range because, like we just showed, our equivalence point is going to be somewhere in the basic area. So I'm going to end part 2 here, and then in part 3 we're going to switch gears and we're going to talk about solubility of ionic compounds.